Imagine predicting the existence of a fundamental building block of reality 37 years before anyone could actually build it. That's exactly what happened in 1971, when a brilliant mathematician named Leon Chua looked at the elegant symmetry of electrical circuits and realized something was missing. Today, that missing piece is revolutionizing how we think about artificial intelligence and could slash the energy consumption of our digital world by a factor of 100. Welcome to Mindcast. I'm your host, Will, and today we're diving deep into the memristor revolution, a story that spans 5 decades, from mathematical prophecy to cutting-edge AI chips. We'll explore how this fourth circuit element went from theoretical curiosity to the foundation of brain-inspired computing. And by the end, you'll understand why some of the world's biggest tech companies are betting billions that memristors will solve one of computing's most fundamental problems. Let's start with a question that sounds almost philosophical. What makes something fundamental to reality? In electronics, we had 3 basic components for over a century: the resistor, which resists electrical flow, the capacitor, which stores electrical charge, and the inductor, which stores magnetic energy. These 3 components defined how we build every electronic device, from your smartphone to supercomputers. But Leon Chua, a professor at UC Berkeley, noticed something elegant and troubling. In electrical theory, we have 4 fundamental variables: current, voltage, charge, and magnetic flux. That gives us 6 possible relationships between these variables. 5 of these relationships were accounted for by our 3 components and basic physics laws. But one relationship, between charge and magnetic flux, had no corresponding physical component. Think about this for a moment. In physics, when we find mathematical symmetries, they usually point to real phenomena in the universe. Einstein's equations predicted black holes decades before we observed them. Antimatter was predicted mathematically before it was discovered. Chua realized that this missing relationship suggested there should be a 4th fundamental circuit element. He called it the memristor, a combination of memory and resistor. Here's what made Chua's prediction so radical. Unlike a regular resistor, which always has the same resistance, a memristor would remember its history. The more electrical charge you push through it in one direction, the easier it would become to push charge through it again. Push charge the other way, and it would become more resistant. When you turned off the power, it would freeze in place, remembering exactly what state it was in. But here's the thing. This was 1971. The idea was brilliant, but the technology to build something that small and precise simply didn't exist. So, for 37 years, the memristor remained a beautiful mathematical concept with no physical reality. Scientists occasionally wondered about it, but the world moved on. Silicon transistors were getting smaller and faster every year following Moore's law. Why chase after theoretical components when traditional electronics were working so well? Fast forward to 2008. At Hewlett-Packard Labs in Palo Alto, a team led by Stan Williams wasn't trying to prove circuit theory, they were trying to build better computer memory. They were working with incredibly thin films of titanium dioxide, just a few atoms thick, sandwiched between metal electrodes. These were experimental memory devices, part of HP's quest to create something faster than hard drives, but more permanent than RAM. But something strange was happening in their lab results. When they applied voltage to these tiny devices, the resistance would change and stay changed. Even more puzzling, when they plotted the current versus voltage over time, they got these distinctive figure 8 patterns. These weren't behaving like any component they knew. That's when Dmitry Strukov, one of the HP researchers, made the connection that changed everything. He recognized those figure-8 patterns from his graduate studies in circuit theory. They matched exactly what Leon Chua had predicted a memristor would do. After 37 years, they had accidentally built the missing circuit element. But how does this actually work? Picture the titanium dioxide film as a tiny highway with two lanes. One lane is made of perfect titanium dioxide. It's like a traffic jam, very hard for electrons to get through. The other lane is missing some oxygen atoms, creating what we call oxygen vacancies. This lane is like a wide-open freeway. Electrons can zip through easily. Here's the magic. When you apply voltage, you can actually push that boundary between the two lanes. Push it one way, and you get more of the easy, conductive lane, lower resistance. Push it the other way, and you get more of the difficult, resistive lane, higher resistance. When you turn off the voltage, those oxygen vacancies stay exactly where you left them. The device literally remembers what you did to it.
The HP discovery made headlines around the world. Finally, the missing piece of circuit theory was found. HP immediately started talking about universal memory. Imagine a single type of memory chip that was as fast as the cache in your processor, as dense as your hard drive, and never forgot anything when the power went out. It seemed like memristors would revolutionize computing overnight.
But sometimes, the most important discoveries take time to find their true purpose. While engineers struggled with the manufacturing challenges of making reliable memristor memory chips, a completely different revolution was brewing. Artificial intelligence was exploding, and with it came a desperate need for more efficient computing. This brings us to one of the most fascinating parallels in technology. Memristors don't just act like electronic memory devices. They act remarkably like biological synapses. Think about how your brain works. Each neuron connects to thousands of others through synapses. When you learn something new, those synaptic connections get stronger or weaker based on experience. Frequently used pathways become easier to activate, just like a memristor becoming more conductive. But here's what makes this truly revolutionary. In your brain, memory and processing happen in the same place. When you see a face and recognize it as your friend, you're not shuttling data back and forth between a memory department and a processing department in your brain. The recognition happens right at the synapses where the memory is stored. Traditional computers are built completely differently. They follow what's called the von Neumann architecture. Memory's over here, the processor's over there, and they talk to each other through a data bus. Every single calculation requires fetching data from memory, processing it, and sending results back. It's like having to run to the library every time you want to remember a phone number while you're doing math. This inefficiency has become a massive problem for AI. Modern neural networks have billions or even trillions of parameters, the weights that determine how the network responds to inputs. In a traditional computer, training a large language model requires constantly moving these weights back and forth between memory and processors. The energy cost of just moving that data can be hundreds of times larger than the actual computation. Memristors offer a radically different approach called analog in-memory computing. Instead of storing weights as digital bits in separate memory chips, you store them as resistance values in memristor arrays. When you want to multiply an input by a weight, which is the core operation in neural networks, you just apply the input as a voltage and read the current. Ohm's law does the multiplication for you instantly, right where the weight is stored. The energy savings are staggering. Companies like TetraMem and Rain Neuromorphics are claiming efficiency improvements of 100 times or more compared to traditional processors. That means AI models that today require entire data centers could potentially run on battery-powered devices. Imagine having GPT-level intelligence in your phone, running all day without draining the battery. But the story doesn't end with efficiency gains. Researchers have discovered that memristors can implement learning algorithms that are impossible with traditional digital circuits. There's something called spike timing dependent plasticity. It's how biological neurons learn by adjusting connection strength based on the precise timing of neural spikes. In a traditional computer, implementing this kind of learning requires complex software and thousands of transistors per connection. But with carefully designed voltage pulses, a single memristor can automatically implement this learning rule through pure physics. The device literally learns by experiencing patterns in its input, just like a biological synapse. So, where does this leave us in 2025? The field has exploded into a fascinating ecosystem. Tetramem, founded by former HP researchers, is shipping commercial chips that integrate memristor arrays with conventional processors. Rain Neuromorphics is pursuing an even more radical approach, building processors that work more like biological networks than traditional computers. IBM continues to push the boundaries with their phase-change memory approach, while companies like Mythic are taking the pragmatic route of using existing flash memory in novel ways to achieve memristor-like behavior. Even HP has pivoted their approach, moving from universal memory to specialized AI accelerators. But challenges remain. Manufacturing memristors with consistent, precise resistance values is still difficult. The analog nature of these devices makes them sensitive to temperature, aging, and manufacturing variations. And perhaps most importantly, we need new software tools and programming paradigms to take full advantage of neuromorphic hardware. So, what should you take away from this incredible 50-year journey? First, pay attention to elegant mathematical predictions, even when they seem impossible to build. Leon Chua's insight about circuit symmetry took nearly 4 decades to pay off, but when it did, it opened up entirely new possibilities for computing. Second, the most important discoveries often find their true purpose in unexpected ways. Memristors were discovered in pursuit of better memory, but their killer application turned out to be brain-inspired computing. Sometimes the technology needs time to find its perfect match with a real-world problem. And third, when we're facing seemingly impossible challenges, like the energy demands of artificial intelligence, the solution often comes from fundamentally rethinking our approach. Instead of building faster traditional processors, memristors suggest we should build processors that work more like biological brains. The memristor revolution is just beginning. As AI becomes more central to our daily lives, the need for efficient, brain-inspired computing will only grow. What started as an elegant mathematical insight in 1971 may well become the foundation for the next era of intelligent machines. That's all for today's Mindcast. If this deep dive into memristors sparked your curiosity, I'd love to hear your thoughts. What other missing elements might be waiting for us to discover? Until next time, keep questioning, keep learning, and remember, sometimes the most profound technologies start with someone noticing what's not there.